Bismillahirrahmanirrahim. So in the previous class, if you remember, we discussed about the refrigerator, the efficiency of a refrigerator, coefficient of performance, then entropy, and today we are going to discuss about the change of entropy in reversible and irreversible process. So before I start our today's topic, I want to ask, do you have any question regarding this refrigerator or entropy? Because as I remember, I told you to go through the lines of the book. I gave you the idea by lecture, but I told you to go through the paragraphs that are written in the book so that you have a clear idea. So did you go through?
Yes.
Any doubt, any question you want to ask? Or we can just move forward?
We can move forward.
Okay, we can go forward. So change of entropy in reversible and irreversible process. So at first we need to revise the idea of reversible and irreversible process a little bit. If you remember, the reversible process is a one which can be traced back to the original position. Okay, but in irreversible process, some kind of heat loss or energy loss will be there, and as a result, what will happen? We cannot actually get back to the original position following the same path. Okay, Acha. So change of entropy in reversible process. Let us see what does it say. Carnot cycle is a reversible cycle, right? Because we get back to the original point. In figure 1.15, ABCD is a Carnot cycle. Yes, the figure of Carnot cycle has been drawn. So let me draw it on the board. PV diagram. Okay. Now this is the isothermal process. The temperature remains constant, but this is not adiabatic because heat exchange is taking place. Then this is an adiabatic process. No heat transfer will take place. That means the temperature may change. And then again, this is another isothermal process where the temperature is kept constant as T2. And then again, this is another adiabatic process. So if you remember, this is isothermal expansion because the volume is expanding. And again, so AB is isothermal expansion from B to C. This is adiabatic expansion because still the volume is expanding. Then again from C to D, this is isothermal compression because the volume is decreasing. And from D to A, another further decrease of volume. So we can say this is adiabatic compression. Okay. So this is our Carnot cycle and this is a reversible process. From the Carnot cycle, it is seen that AB is an isothermal expansion. I already told you, and CD is an isothermal compression. AB and CD, both are isothermal process. Again, BC is an adiabatic expansion. BC adiabatic expansion and DA is adiabatic compression. Now, as BC and DA are adiabatic curve, so there will be no change of heat along them. As a result, there is no change of entropy of the working substance. This is also something we discussed in the last class, that if there is no heat exchange, no question of entropy change will appear. No heat transfer, then no change of entropy. The entropy remains the same. Okay, so entropy varies with the exchange of heat. If you lose it, entropy changes. If you gain heat, entropy changes. Okay, other than that, entropy will not change. So we are not talking about the entropy change for BC and DA part. We will talk about the change of entropy in case of AB and CD part only, where the heat exchange can take place. So you see the change of entropy along the isotherm AB. Yes, isotherm AB along this line. What is the change of this? So along AB, what is the change of entropy? If you see, let us say I supply Q1 amount of heat, and the temperature here I have kept constant as T1. So Q by T, this is the change of entropy, right? Along the isothermal process AB. This is not AB is equal to the change of entropy along AB. Okay. Similarly, what I can write about the change of entropy along CD, I can write it minus Q2 divided by T2 because Q2 amount of heat is being lost and T2 is the temperature at which we are keeping the temperature constant at. Okay. Now why it is minus? Because it is decrease. Whenever I will give minus, it will show a decrease. Okay. So along AB, this is the change. Along CD, this is the change. Now, if I ask you throughout the process, what is the total change? Then what you will do is the total change of entropy of the working substance, that is del S. It is going to be that Q1 T1 minus Q2 T2. Now, if you remember equation number 1.49, page number 28, equation number 1.49. What does it say? It says that Q1 by T1 is equal to Q2 by T2. Okay. So if both of them are equal to each other, then their difference is going to be 0. That means the difference in entropy for a reversible process is going to be 0. Okay. We already saw that without any calculation, we know that BC along BC and DA, there is not going to be any entropy change. And along AB and CD, we found that here also there is no entropy change. So for reversible process, we can say that there will be no change of entropy. Now you might ask, sir, you said that there is going to be change of entropy along AB and CD. Yes, there is going to be change, but they are balancing each other. Like if the entropy increases by a certain amount through the process AB, now along the process CD, it is decreasing by the same amount. So if it is increasing by an amount and decreasing by the same amount, so it is coming back to its original position only, right? So as a result, what is happening throughout the whole system, throughout the whole process or Carnot cycle, we can say that there is no change of entropy. Is the point clear?
Yes, sir.
Yes.
Okay. So now we will take a look at the change of entropy in irreversible process. Change of entropy in irreversible process. Again, in an irreversible process, the entropy does not remain constant. Yes. Okay. Let two objects completely isolated from the environment are in contact with each other. Okay. So this is an isolated system. In isolated system, we cannot provide any heat. We cannot take any heat from the system. Okay. Achha. Now, if both the body are in contact with each other, then what will happen? The temperature of the two objects are respectively T1 and T2. That means there are some temperature difference between them. And T1 is considered to be greater than T2. Then what will happen? The heat will flow from the warm object to the colder object. Okay. That is, the warm object loses dq amount of heat. Oh, sorry, I missed a line. Let within a very short period of time. So short period of heat will be transferred. Okay. So that short amount is considered to be dq. dq amount of heat is transferred from the warm one to the cold one. Okay. That is, the warm object will lose dq amount of heat and the colder object will gain dq amount of heat. Is it okay?
Yes.
Rifat, are you there?
স্যার একটু আবার বলেন।
আচ্ছা, আমি যদি তোমাকে 5 টাকা দেই, আমার থেকে 5 টাকা কমে যাবে, তোমার কতটুকু ইনক্রিজ হবে? তুমি কতটুকু রিসিভ করবা?
5 টাকা বেশি।
বিবি হাওয়া, তুমি কোশ্চেন করছো না, তুমি আমাকে রিপ্লাই দাও। আমি যদি তোমাকে
স্যার আবার বলেন দেখি।
আমার থেকে 5 টাকা কমে যাবে, তোমার কত টাকা বাড়বে? আমি যদি বুঝি না 5 পেটি দেই, ঠিক আছে, তাইলে আমার যতটুকু টাকা ছিল সেখান থেকে 5 পেটি কমে যাবে না?
জি।
আর তোমাকে যেহেতু আমি দিয়ে দিছি, তোমার যতটুকু টাকা ছিল সেখান থেকে 5 পেটি বেড়ে যাবে না?
জি।
তো তাইলে আমি যতটুকু লুজ করব, তোমার ঠিক ততটুকু বেড়ে যাবে। এতটুকু বুঝতে পারছো? অথবা আমি যতটুকু নিব, তুমি ঠিক ততটুকুই নিবা। তো এখানে আসলে টাকার জায়গায় তুমি চিন্তা করো যে অ্যামাউন্ট অফ হিট, একটা হচ্ছে হট অবজেক্ট আর একটা হচ্ছে কোল্ড অবজেক্ট। হট অবজেক্টটা হিট দিবে, ও যতটুকু হিট দিবে, কোল্ড অবজেক্টটা ঠিক ততটুকুই হিট নিবে। কারেক্ট? তো আমরা বলতেছি যে এখানে within a very short period of time, dq amount of heat will be given up by the hot object. The same dq amount of heat will be received by the cold object. এটাই ওরা এখানে বলছে, দেখো। That is, the warm object loses dq amount of heat and the cold object gains dq amount of heat. একজন যতটুকু লুজ করবে আরেকজন ঠিক ততটুকুই গেইন করবে। ওকে, ক্লিয়ার এতটুকু পর্যন্ত?
Yes.
আচ্ছা, now
জি স্যার।
therefore minus dq by d1 is the decrease of entropy of the worm object. এখন worm object এর entropy change we are calculating for worm object. For worm object we are saying the change of entropy is minus dq by d1. Why minus? Can anybody tell me why minus?
Because the heat decreases.
Decreasing. Okay, worm object is losing the heat, so it will decrease. The entropy will decrease. As a result, we will show it by putting a minus. Now, in case of cooled object, what is going to happen? It is going to achieve some heat, so the entropy will increase, and as a result, for the cooled object, the change of entropy is going to be dq by T2. Okay, because the temperature of cold object is T2, and the amount of heat supplied is dq. Okay, and it is going to be positive because it is gaining heat, increasing the increase in entropy of the cold object. So therefore the change of entropy of the system, the change of entropy, that is ds of the system, it is going to be minus dq by t1 plus dq by t2. Okay, this one will be minus for the warm object and this is the cold object, and it will be positive. Now if you see, we already told you. Now from here actually there is a possibility of three cases, right? The first one, the change might be positive. That means after you add and subtract, all this calculation is done, then the result might be positive, the result might be negative, the result might be zero. Now what is the result we want to know? Okay, we from here we will not be able to calculate the exact value because we do not know the value of t1, t2 and dq, but we can get an idea that whether the result will be positive, negative, or what. Okay, so we will take a look. Now t1, I already said that it is greater than t2. It is the temperature of the warm object. Okay, so if t1 is greater, can anybody tell me whether dq by t1 will be greater or smaller?
Greater.
Greater.
Smaller, sir. Divide করতেছে।
Definitely it will be smaller. If the denominator is greater, the fraction becomes smaller and smaller. Let me show you in this way. একটা পিজ্জাকে তুমি যদি দুই ভাগ করো, প্রত্যেকটা পিস একটা সার্টেন অ্যামাউন্ট হবে, তাই না? যদি সেম একটা পিজ্জাকে আমরা তিন ভাগ করি, পিসগুলো ছোট ছোট হবে না আরো? দ্যাট মিন্স ডিনোমিনেটর যত বাড়তে থাকবে, তুমি একটা পিজ্জাকে এখন চার ভাগ করো, প্রতিটা পিস আরো ছোট ছোট হয়ে যাবে। That means if the denominator becomes greater, the fraction becomes smaller. Correct or not?
Yes.
Yes. So here I am saying that T1 is greater. That means the denominator of this one is greater. So as a result, this fraction will be smaller, and this denominator is smaller. Okay, T2 is smaller. So dq by T2 will be bigger, greater. So out of these two, what I can see, the positive amount is greater and the negative amount is smaller. As a result, the result is going to be positive, zero, or negative. What it is going to be?
Positive.
Definitely it is going to be positive. Okay, so I can write at least this much. ds is going to be greater than 0, even not equal to 0. 0 equal to হবে না, 0 equal to they must be equal to each other, and they will be equal to each other only when t1 is equal to t2, because dq তো same t1 t2 যদি একটা equal হয় তখনই ds কি হবে, equal to 0 হবে. But here we have already considered that t1 is greater than t2. There is some temperature difference. Okay, so that is why t1 is not equal to t2, and as a result they cannot actually balance each other, so 0 is not possible. Okay, minus is also not possible because this fraction is smaller and this fraction is greater, because the denominator here is smaller. So I hope this is clear. So in case of irreversible process, the change of entropy of the system is going to be a positive value. Anybody has any doubt regarding this?
No.
Okay,
No, sir.
fine. So let us go to the next page, page number 34, the very last page of this chapter. Theoretical, after that there is a numerical example. Okay, so everything in nature tries to acquire the state of equilibrium. This is very true. Whenever an object is hot, if you keep it in the open environment, it chooses to liberate the heat and become it tries to achieve a condition of thermal equilibrium with the environment. It wants to become with the same temperature of the environment. Okay, acha. as a system goes towards equilibrium, the possibility of getting work from the system reduces, right? So as you achieve towards the equilibrium, what will happen? Okay, no, the possibility of work done will be reduced, right? Now, when it attains the equilibrium, no work is found. No one is doing any work. If there is temperature difference, then what will happen? There is a possibility that the system is doing some work on the environment, or the environment might do some work on the system. Possibility. But if it is thermal equilibrium, nobody will do any work on anyone. Okay. So the disability of converting the energy is known as entropy. This is what we studied in the last class. As the system proceeds towards the equilibrium, their entropy also increases. Yes, this is very true. You can see that uh, uh, as I already told you that as the condition or the system advances towards the thermal equilibrium, it loses the capability of doing any work. So the disability of doing any work, it is entropy, right? So as ability decreases, disability increases. Understood? Okay. As the ability is decreasing, ability to do some work is decreasing. So disability is increasing, and disability is entropy. So we can say that as the system advances towards the thermal equilibrium, the entropy of the system increases. Okay. The entropy of a system becomes maximum when we do not get any work from it. The disability peaks that time. Okay, it is the highest, it's the highest value. So that time we can say that that is the highest entropy. Okay, so the entropy of a system becomes maximum when we do not get any work from it. Okay, all spontaneous changes are directed towards equilibrium. Therefore, in case of all spontaneous change, what we mean by spontaneous change? The change for which you do not have to do anything. It is spontaneous. You keep an object here, it is liberating heat and it is achieving thermal equilibrium with the environment. Do you have to do anything? You don't have to do anything. You don't have to make any arrangement or start an engine or something. You don't have to do anything. You don't have to provide it any help. It will just achieve the thermal equilibrium on its own. So this is a process, spontaneous. Okay, and the change that is occurring here is a spontaneous change. So in every spontaneous change, all of the system in the world, they try to achieve the thermal equilibrium. So as a result, what we can say? In the all spontaneous change, the entropy increases because it is going towards the thermal equilibrium. The disability is increasing. Ability is decreasing, disability is increasing. So as a result, the entropy also increases. So this is what they are trying to say. Therefore, in case of all spontaneous change, the entropy increased. Since everything in nature wants to attain equilibrium, so the entropy of nature is gradually increasing. When the entropy of the universe will reach the highest point, when the entropy of the universe will reach at the highest point, then everything will reach the same temperature.
Sir, third line ekটু আবার বুঝাবেন? This disability of converting the energy is known as entropy. Sir, কেমনে এটা একটু
entropy বলো।
হ্যাঁ,
entropy জিনিসটা
এটা কি স্যার ভালো মতো কনসেপ্টটা বুঝিনি আমি এন্ট্রপিটা।
আচ্ছা, এন্ট্রপির আইডিয়াটা এরকম ছিল, আমি আরেকবার একটু তোমাদেরকে রিভাইজ করে, অসুবিধা নাই। আমি তোমাদেরকে বলছিলাম যে যখনই আমরা এতদিন পর্যন্ত কি জানতাম, যতক্ষণ পর্যন্ত আমরা এন্ট্রপির এই টপিকটা পড়ি নাই, we used to know that if we have energy we can do some work, because energy is ability to do some work. This is the basic definition of energy, right? If you have energy you can do some work. But when we started studying the topic of entropy, we saw that even though we possessed some certain amount of energy, we were not able to convert it into work. Now if you remember, we actually gave an example. I don't know whether it will be okay to discuss that example again or not. তুমি আমি যেটা বলবো, এই যে 1.17 যে আর্টিকেল 31 পেজ থেকে 32, এই যে এনট্রপি ডেফিনিশনের আগ পর্যন্ত যে প্যারাগ্রাফটা, এখানে আসলে একটা एग्जांपल দেয়া আছে। ঠিক আছে, এই एग्जांपलটা যদি পড়ো তাইলে তুমি বুঝবা যে even though we have energy we will not be able to do some work. আমরা এই এনার্জিটাকে কোনো ওয়ার্কে কনভার্ট করতে পারবো না। এই যে একটা ডিসএবিলিটি, তুমি পারতেছো না, সেটা তো একটা ডিসএবিলিটি, তাই না? অ্যাবিলিটির অপোজিট। সো ডিসএবিলিটি, এই ডিসএবিলিটিটাকে বলা হয় হচ্ছে এনট্রপি অফ দ্য সিস্টেম। কোন একটা সিস্টেমে যদি এনার্জি আছে বাট সেটাকে ওয়ার্কে কনভার্ট করার ক্ষমতাটা কমে যায়, তাইলে সেটা বলবো যে আমরা এনট্রপি বেড়ে গেছে। ডিসএবিলিটি বেড়ে গেছে, এটা
স্যার
ডিসেবল, সো এটার এনট্রপি বেড়ে যাচ্ছে। তো এখন থার্মাল ইকুইলিব্রিয়ামের কথা চিন্তা করো, যে কোনো একটা স্পন্টেনিয়াস চেঞ্জ, তুমি একটা যে অবজেক্টকে খোলামেলা জায়গায় রেখে দাও, it will radiate the heat and it will try to attain the thermal equilibrium, right? So as এটা থার্মাল ইকুইলিব্রিয়ামের দিকে যত অ্যাডভান্স হবে তত কি হবে দেখি বলো তো, এটার কাজ করার অ্যাবিলিটি কমতে থাকবে, যতক্ষণ টেম্পারেচার ডিফারেন্স থাকে ততক্ষণই শুধুমাত্র কাজ করা যাবে। তো যখন থার্মাল ইকুইলিব্রিয়াম অ্যাচিভ হয়ে যাবে তখন কি হবে, আমাদের কাজ করার অ্যাবিলিটি আর থাকবে না। তো কাজ করার অ্যাবিলিটি থাকবে না, তার মানে ডিসএবিলিটি এখন আছে। abilityর opposite is disability. So as we are losing the ability to convert heat into work, the disability is increasing. So the disability is entropy. So as we can say, the entropy actually increasing. Okay, so যত আমরা থার্মাল ইকুইলিব্রিয়ামের দিকে যাব, ability কমতে থাকবে, disability বাড়তে থাকবে। disabilityটা হচ্ছে এনট্রপি, তো এনট্রপি বাড়তে থাকবে। সরাসরি আমরা যদি এখন কানেক্ট করি থার্মাল ইকুইলিব্রিয়ামের সাথে এনট্রপি, আমরা বলতে পারবো যত আমরা থার্মাল ইকুইলিব্রিয়ামের দিকে যাব তত আমাদের এনট্রপি বাড়তে থাকবে। থার্মাল ইকুইলিব্রিয়াম যখন অ্যাটেইন করে ফেলবো তখন কি হবে দেখি বলো তো, তখন এনট্রপি উইল বি দ্য হাইয়েস্ট। এখন টোটাল ইউনিভার্সের কথা চিন্তা করো, ইউনিভার্সের প্রত্যেকটা অবজেক্টের মধ্যে টেম্পারেচার ডিফারেন্স আছে, তাই না? এই কারণে কেউ না কেউ কারো না কারোর উপর কোনো কাজ করতে পারতেছে, দ্যাট মিন্স দে হ্যাভ দ্য অ্যাবিলিটি টু ডু ওয়ার্ক, সো এনট্রপি ইজ লেস। বাট if you imagine a situation where all the objects in this universe are at thermal equilibrium with each other, all the objects are at thermal equilibrium with each other, if this situation arises, what is going to happen? The ability will be minimum, the ability of doing work will become zero. Why it will become zero? Because thermal equilibrium has been achieved, all the objects are in thermal equilibrium with each other, no temperature difference is there, so nobody has any ability to do any work. So that means no ability means highest disability, that means highest entropy. This is the highest entropy that we can imagine, the highest disability, when all the object will become at when all the object will achieve a condition when it is at thermal equilibrium with all other objects. That means the temperature of all the object that is in the universe has become same. So that is actually, that situation is given a special name. We will try to know that name in a bit. Okay, so you see, when entropy of the universe will reach the highest point, then everything will attain the same temperature, that means the thermal equilibrium. As a result, heat energy will not be possible to convert into mechanical energy, because we are at thermal equilibrium, no heat can be converted, the ability has been finished. Okay, this state of universe is so called heat death of universe. Very important concept, might come for 2 mark question. Okay, acha. So I hope you understand the heat death of the universe. By this we mean that no heat energy transfer will take place, because all the objects are at thermal equilibrium with each other. So if they are all at same temperature, no heat is going to be flown from anybody to another body, because we know that to get the heat flow, the temperature difference must be there. So if every object are at thermal equilibrium, no heat temperature difference is there, no heat flow. So as a result, this is heat death. This situation is called heat death of the universe. Anybody has any doubt?
No.
Okay. Now change of entropy at every step of Carnot cycle. I guess I already discussed this. Yeah, this is the same thing. See, at the first step they say the isothermal. Oh, so isothermal step it will be Q1 by T1. In the adiabatic expansion, it is going to be 0. In the isothermal compression, it is going to be minus Q2 divided by T2, and in adiabatic compression, it is going to be 0 again. So they have actually repeated the same thing. I hope if you go through this, you will be able to understand it. Okay. Acha. Then we have the very last topic of this chapter, which is entropy and disorder. Okay, entropy and disorder are inseparable. Okay, why? With the increase of entropy of a system, as the possibility of getting work from the system is reduced, entropy increases, means disability increases. Disability increases means ability goes down. So ability of getting any work is decreasing. So as well as disorderness of the system increases. Okay, so this one we can understand. If we cannot get any work from any machine, you understand the amount of disorderness that will be caused due to this situation, right? We can explain it with an example. Okay, keeping some salt in a glass. Okay, if we pour water into the glass, then the salt will go on dissolving and the molecular ions of the salt will spread all around the solution randomly. Yes, means গলে যাবে, আমরা যেটাকে বলি গুলে যায়, লবণ গুলে যায়. Okay, in the solid state the ions of the salt are arranged in a regular fashion. Though the salt is heavier than the water, instead of depositing at the bottom of the glass, it spreads out all around. And when the salt spreads out all around in the solution, we say that the solution has achieved the equilibrium state. Yes, when the solution achieves the equilibrium state, the molecules are most disordered, right? They have broken down. In the solid state, they were in an arranged order, but when it has been when it is getting dissolved into the liquid, it is not arranged in a proper way. It is randomly arranged. Okay, so disorderness is caused. No order is there. This is why entropy is called measure of disorderliness. Okay, if the entropy is high, we can say the disorderliness is also high. Okay, so that is why entropy is called the measure of disorderliness. Through entropy we can measure this. That is, if we try to bring orderness of a system by applying force on the system, then the entropy of the system will be reduced. Yes, we must decrease the disability, or we can say we must decrease the entropy to reduce the disorderness, and so that we can get some work from the heat energy. That means we can convert some energy into work. Okay. When a substance in a crystalline state, then its molecules are arranged in a regular orderly fashion. Now, to be honest, I actually don't possess much knowledge about this crystalline state. Okay, I'm a little bit. Last example. আমি এখনো পড়ি নাই, সেটা তুমি পড়ে ফেলছো? আচ্ছা, ওকে, আমি যাচ্ছি দেখতে। তো এখানে যেটা বলছে কি, for this reason the entropy of solid substance is less. Entropy is less. That means in solid substance there is possibility to do some work. It can be compared with the parading soldiers or students listening lecture in a class. Here entropy is low. Okay, but when the parade is over or the teacher leaves the class, as the bell rings, the student becomes indisciplined and the entropy increases. আসলে খুব ইন্টারেস্টিং একটা কথা বলছেন। So when the teacher is in the class, you are like solid state, arranged. You are sitting in an arranged way, right? But as soon as the teacher leaves, you are, you break the discipline and become indisciplined, and as a result, disorderness is caused, which we can say, according to physics, the entropy is increased. Okay. So alhamdulillah, we successfully finished the chapter thermodynamics. This is one of my very favorite chapter. I don't know how much well I could explain. Now I would like to request you to go through the numerical example that are left here, and as well as start solving the solution group problems. Okay, because in grade 12 we have very less amount of time, so as fast as you can do that, we can go to our next chapter. So what I will do is, you will continue solving this problem and we will start. Yes, Aisha, কিছু বলবা?
স্যার আগে আপনি শেষ করেন, পরে বলবো।
হ্যাঁ,
আগে আপনি কথা বলা শেষ করেন, এর পরে বলবো।
ওকে, তো তাইলে যেটা বলতেছিলাম যে আমরা ইলেকট্রোস্ট্যাটিক, এই চ্যাপ্টারটা আসলে তোমরা কিন্তু পড়ে আসছো, স্ট্যাটিক ইলেকট্রিসিটি, এটা গ্রেড 10 এ পড়ছো তোমরা। তো আমরা এইখানের যে ইজি কনসেপ্টগুলো আছে যেগুলো আমরা পারি, আমরা ওগুলোর ব্যাপারে কথা বলতে থাকবো। So that will take, I hope 1 or 2 days. So within that, try to finish the numerical example. I know creative solution is not possible within this amount of time. So let us fix a time. Okay, let us fix the Sunday, next Sunday. And inshallah, next Sunday, inshallah, we will discuss about the doubt of numerical example if you have any, and the doubt regarding the solution of solution book creative. Okay, and also one thing,
suggestion book 9. Suggestion book 9.
Okay, even if the suggestion book is not there, you can actually download the PDF. If you want, I can download the PDF for you and give it. Okay. So I will give you the PDF. From the PDF, actually, you can study, no problem. Nothing should be stopping us, okay? So also I remember that we actually didn't hold a solution class about the doubt of the last chapter, that is ideal gas. Like করছিলাম, still I forgot. করি নাই না? So তাইলে আমাদের ওইটার ব্যাপারে আসলে একটা ডিসিশন নিতে হবে যে ওইটা ক্লাসটা আমরা কখন করব। তো গ্রুপে আমরা এটা নিয়ে একটু ডিসকাস করব, ওকে? আচ্ছা আয়েশা,
স্যার
বলতে চাইছিলাম, হ্যাঁ
স্যার 1.19 এ আমার একটা ডাউট ছিল, এটা আজ করতে চাইছি।
1.19, আচ্ছা ঠিক আছে, তুমি 1.19 এ গেছো, মাশাআল্লাহ, গুড গুড। এখানে কি ডাউট বলো তো? What will be the change in entropy to convert 5 kg ice at 0 degree to water at 100 degree Celsius? আচ্ছা, specific latent heat of fusion, তার মানে হচ্ছে আইস গলার জন্য যতটুকু হিট লাগে 336.000, ওকে? Specific heat of water is 40, হ্যাঁ এটা তো আমরা জানি, ওকে? তো এখানে বলছে যে what will be the change in entropy, তো এনট্রপি কত সেটা বের করার জন্য আমাদের dq লাগবে। তো এখানে ওকে, এখানে কি বোঝা নাই বলো? আমার তো খুব ইজি লাগছে।
স্যার ওই যে লাস্টে দিয়ে বাট হিয়ার দা অ্যাবসর্বড হিট, ওইখানে কি করছে ওগুলো আমি বুঝি নাই।
পেজ নাম্বার 44
হ্যাঁ হ্যাঁ আমি দেখতেছি এটা।
ইন্টিগ্রেট দেখো।
In entropy to convert temperature eta, but here the absorbed heat dq is equal to mx eta. এখানে dq এর ভ্যালু বসাইছে, তো এটাই দেখতে পাচ্ছি। দেখো এখানে যখন when we will convert, আচ্ছা এটা একটু লিখে বুঝাতে হবে। Let us say we have 0 degree Celsius ice and we want to attain 100 degree Celsius of water. This is a two-step process. At first, you need to convert this 0 degree Celsius ice to 0 degree Celsius water. That is the melting of ice, right? Then you have to heat the water to raise the temperature from 0 degree to 100 degree Celsius. So you can see the change of entropy or the change of heat, the supply of heat has to be in two steps. At first, here the entropy, if I want to calculate the change of entropy del S1 is going to be equal to dq by T, because the temperature here is going to be 0. It is going to remain at 0. So here dq, the heat absorbed, here the heat absorbed is going to be mLr. If you remember, we already discussed this in effect of heat on matter in SSC level, okay?
Yeah.
Because here no temperature difference, right? Generally we know this equation of Q, that is ms del theta or del T. Now this is applicable when the temperature is changing. So we will apply this formula in this state. Okay, for here we will apply this formula, that is okay. But what about this step? In this step, no temperature change is occurring. So when temperature is not changing, if you remember, the state change occurs, right? Here the temperature is not changing. That means the state is being changed. Whatever the energy you are supplying, it is not being used to increase the temperature. Then it is being used to change the state. Yes, the state is being changed from ice to water. So in such case, if you want to calculate the amount of heat supplied, you need to multiply the mass and the latent heat. Now latent heat of fusion, if it is melting, but if it is the water is converting to vapor, then that will be latent heat of vaporization. You should actually know this already. I don't know, maybe you forgot. Okay. Now here, if I want to calculate del S2, it will be equal to dq by T. Now here dq, what is dq? Now dq is equal to ms dt.
Yes.
It is a small amount of heat we are considering, we can say dt. Okay, so we will just replace it here, ms dt by T. Now we are heating it from 0 degree to 100 degree Celsius, right? So we are actually have a lower limit T1, we have an upper limit T2. So here also I will replace T1 to T2. Now ms, this is constant, this will come out, and as a result what will happen, dt by T it will be T2 T1. So this one, if you remember, if we integrate it, ln T is going to come according to the formula. Can you see the writing on the board, because I think the marker got faded? So ns,
Yes, we can see.
it will be ln T. We actually did a similar calculation while starting the theory part. So from here I can write ms ln T2 minus ln T1. Okay, now as it is minus, we can write ns ln T2 minus T1. Okay, so here actually we will replace the value of water. See, for water it is the temperature increase of water, so mass is 5 kg, and specificity of water, that is 4200 joule per kg per Kelvin. T2 is 100 degrees Celsius. Actually not 100 degrees Celsius, this one has to be converted to Kelvin, so it will be 373
373.
and T1 it is
273.
273 Kelvin. Okay, so as you can see, we have all the value needed, so we can calculate the dq here, and we know the d, so we can easily sorry, from here actually this is enough. If you do the calculation of this part, that will give you the change of entropy, right?
Okay, sir.
Okay, ইরফান তুমি কিছু বলতে চাইছিলা?
স্যার
বলো।
স্যার 5 মিনিট ওভার হয়ে গেছে।